potential. Now we give the conclusion today, the resting membrane potential. So as we said, the basics, we learned the basics of this particular area yesterday, and now we are giving the complete information about this. Let me remind you once again, in resting membrane potential, or we may call it as resting membrane potential is said to be minus 70 millivolts, and this is the condition we say polarization. Such condition we call polarization. Okay, so such kind of condition we say polarization. And in the extracellular fluid, we said over that sodium ions are greater in ECF in compare with the exoplasm. This is the exoplasm. And potassium ions are greater. Potassium ions are greater in exoplasm, 30 times greater than the ECF. And voltage wise, when we start discussion about the voltage, that we said the voltage positive outside in the ECF. Okay, so voltage inside is negative. Negative. That means how much negative? That's what we said it as a resting membrane potential. Okay. So to hold the sodium ions outside, to hold the potassium ions inside, we said there is some energy is required over, some energy. That means resting status require energy. Being resting status that require energy. So some energy. So just we are talking about example I gave in the form of 10 ATPs. Some energy we are using to hold the ions not to come in and not to go out. So we need to break that energy. We means that stimulus which we are giving, if it breaks that energy, the stimulus which we are giving, if we break that energy, that impulse can be conducted along the length of the axon. That is the basic you need to remember. Then for that, we made some definitions yesterday. That amount of stimulus energy which is required to conduct an impulse is called as threshold. Amount of stimulus energy required to conduct an impulse is called threshold. Then after we said all the threshold energy above that, all the stimulus energy above the threshold can be conducted as an impulse. All the stimulus energy below the threshold cannot be conducted as an impulse. We said it as none. All or none principle. Okay, so we'll make it a little bit clear here that when stimulus comes, what happens? When stimulus comes, I'll take the next page here to show the resting condition. Okay, so when stimulus comes, what happens? So let me see, let me show you that this is the area minus 70, minus 70, minus 70, minus 70. And I already said to you that the very important basic to remember that influx of sodium ions require that occurs that leads to the charge increases. The flux of potassium ion charge decreases. Okay, so that you remember. And now I am drawing here the sodium ions in the extracellular fluid. The sodium ions. I will draw the potassium here. Potassium. When the stimulus energy comes here, that breaks the energy which is holding the ions outside and inside. That what you said threshold energy, that brings minus 70 will become a minus 55. Minus 70 will become minus 55. That is because of whom? That is because of threshold stimulus. That is because of the stimulus which we are given, that minus 70 will become minus 55. Okay, so that is the first step is happening here. And this minus 55, that means minus 72, what is minus 55? Charge increased or decreased? Charge increased. Minus 70 to minus 55 means charge increased. That increasing charge opens the sodium gates. Sodium gates are open and the voltage or the influx of sodium ions started inside. Influx of sodium ions results the increase in the charge. That charge will increase up to plus 45. Charge will increase up to plus 45. Okay, so I'll show you that condition again. Minus 70, minus 70, minus 70, minus 70 along the length. What happened here? That because of threshold stimulus, what happened? Minus 70 reached to minus 55. Then minus 55. This minus 55 now reached to plus 45. How? That plus 45 because of influx of sodium ions. Because of influx of sodium ions. What do you see this condition as? This condition can be called as depolarization. This condition is said to be depolarization, and that potential energy which is formed here can be called action membrane potential. Depolarization we call the condition, and that is said to be action membrane potential. What next? What next here? This plus 45 will move forward. This plus 45 will move forward. For that I am taking another screen that now along the length we have here plus 45 and minus 70, minus 70, minus 70. So this plus 45 will move forward, will bring minus 70 to minus 55 here. That is the voltage increase. That makes the influx of sodium ion. Then that brings minus 55 now become plus 45. Okay. So now the voltage become here plus 45. Then this plus 45 it has to move forward. Okay, that will move forward. Then before that, when this charge is shifted, when the stimulus is shifted here, what should happen in this area? They need to come towards the normal condition. Okay, so here it is influx of sodium increases the charge. Getting back into the normal condition, we say repolarization. We call it as repolarization. That is happen with the help of efflux of potassium ion. After passing potential energy forward, this area will become normal here. Becoming normal is called as repolarization. That means you came normal here, that is minus 70. Due to the efflux of potassium ion, we said charge will decrease. Isn't it? Charge will decrease. Okay, now we reached back. Then I think afterwards that should come to the normal position, isn't it? But not yet here. So we said minus 70, then plus 45, minus 70, minus 70, minus 70. This area reached to the normal. But there is a danger. This potential energy, whatever forwarded over, that may possible to move, may forward or may backward. Backward in the same place where we are given the stimulus, isn't it? So it may come backward. So that's why to avoid that, still the potassium ions will go on, that voltage is go on to decrease, that we say minus 90, hyperpolarization. Such condition is called as hyperpolarization. That now it facilitates this plus 45 will go only forward, that means minus 70. That brings minus 70 will come to minus 55. That makes the influx of sodium ion. If you practice this for 2 to 3 times, that you can understand. Okay, so that's why let me make it that how does the impulse forward? Just follow me. So I said to you, there is minus 70 along the length. The voltage along the length of axoplasm is minus 70. That you called it as resting membrane potential. Then when the stimulus is given, that stimulus brings the voltage increase. Okay, voltage increase, minus 70 to minus 55 increase, that's not decrease. That means that minus 70 to minus 55, that brings the influx of sodium ion, that brings the voltage increased up to plus 45. Voltage increased up to plus 45. Okay. So now this area is with plus 45. We called it as depolarization. We say it as depolarization. Now it needs to move forward. It needs to move forward. That brings minus 70 to minus 55 here. So what it makes? Influx of sodium ions. That brings minus 55 reaches to plus 45. Okay. After depolarization of this area, after the depolarization of this area need to get back, isn't it? Need to get back. That means this is, oh my god, we lost everything. Okay. So no matter. So this area need to get back. For that, a flux of potassium ions will be helpful for that. That brings up to that plus 45 to will go back to the minus 70, will go back to minus 70. Okay, so that means what do you call it as? What I said it as repolarization, but there is a problem with repolarization. If this area voltage is also minus 70, this voltage may come back. So that means to make it unidirectional, to move it forward only, this area, still potassium ions will go on. And that's why minus 70 will become minus 90. That what do you say? Hyperpolarization. But we call it as hyperpolarization. So finally, the situation will be like this: minus 90 plus 45 minus 70, like this. Okay, so that allows only the impulse will move only forward, because this is not polar, the normal state. This is hyperpolarization more than the rest. Person, imagine he is sitting in this place. So he is sleeping. Hyperpolarization, nothing but sleeping. Okay, so it is very easy to make this person to stand up. Okay, this person is in stand up position. So that's why he preferred to move here. Okay, after all passing, this area reaches to plus 45 and this area will come for minus 90. Okay, so that means this person is stand up now and he has to wake up him. It's just like a co-gain. Okay, so then after this, it will come to normal position. Okay, so seems to be confusing, isn't it? Let's make a complete sequence of this that you can understand. When we give the stimulus, normal condition is minus 70. Okay, when we give the stimulus, that we reach to minus 55. So we call the condition as threshold stimulus, that we say that as threshold stimulus. Okay. Then because of that influx of sodium ions occur, then voltage will increase up to plus 45. We say that condition as depolarization. The depolarization. Okay. Then after all the depolarization, when impulse will make them to move forward, that area will come to normal position again, that we say it as repolarization. We call the condition as repolarization. Okay, next, after the repolarization, it is not going to stop. What it is doing, that again more potassium ion efflux makes over, the area reaches towards the hyperpolarization. Okay, so nowadays these kind of questions are not asking in the Neet, but there is a possibility in the MSET, like this great application will be asked always in MSET. That earlier also we have seen this kind of question here. So that means how do they ask? Let me show you. Let me show you. How do they ask this kind of question? So this is minus 90 minus plus 45 minus 70 minus 70. Okay. So always before the depolarization, this is depolarization, isn't it? Always before the depolarization, area before the depolarization is in hyperpolarized state. Okay, that why it is in hyperpolarized state? That means impulse is unidirectional in the axon. That means they frame a question like the recession reason type of question in axon. Okay, in axon always impulse is unidirectional. Impulse is unidirectional, will move only forward. Why? So can we give the reason for this? Yes, we can give the reason for this. What is the reason for this? The reason is always before the depolarization. What can be expected here? Hyperpolarized state. Always before depolarized state, we can see hyperpolarized state, which facilitates impulse to move forward only, which facilitate the impulse to move forward only. So that's it. So you have to remember this like this. For example, this plus 45 reached here. Here it became plus 45. Okay, when this area became plus 45. So what happens if that area becomes plus 45? This area now will come to minus 90. So it facilitates not to come forward, not to come backward, only to move forward. Then after it will come to normal position. That only I shown in the form of like this. I just shown to you. In the next screen, that okay. Let me show that screen. This is the screen. Minus 70, minus 55, plus 45, minus 70, minus 90. Then reaching back again to the resting state to the resting state. A journey from resting state to the resting state. That we discussed till the time. A journey when I touch an area of any area of the neuron. When I touch, what happened? When I touch, that area will go to the depolarized state. That when I touch, that my touch is said to be threshold. My stimulus is called threshold. That brings some voltage difference. That how much voltage difference it will bring? Minus 70 to minus 55 means it is 15 millivolts plus. Okay. So from here plus minus 55 to plus 45. That how much it will be? Minus 55 to plus 45. That here this is also plus, we can say. That means 45 plus, that we need to bring it over. Okay, minus 55 to plus 45. So how much it will come over? Minus 55 to plus 45. Is there anyone to say this? No, totally you say that why we need to make it like this. We don't get these kind of questions. We get like this. Minus 72 plus 45. Total, we'll make it total. Why? The micro postmortem is not required. Direct, minus 72 plus 45. How much voltage increased? Can anyone say that how much the increase of voltage here? Minus 72 plus 45 means the increase of voltage is 115 millivolts. Okay, little mathematical application. So simply we say I'm asking like minus 5 to plus 5, minus 5 to plus 5. What is the distance I am talking? That means minus 4, minus 3, minus 2, minus 1, then 0, 1, 2, 3, 4, 5. We reach to the 5. So that you need to understand like that. Okay, so that integrations we used to say that you may have learned over in earlier classes that without mass, how we come across that 10th class, that this is the basic mathematics. So that's why simply I am saying here that here 15 millivolts and here 100 millivolts. The total 100 millivolts reaching towards the resting state to the depolarized state, we say 115 millivolts we reach. Okay. Then from the depolarization to the repolarization, reaching normal to back again, repolarization. Then 10, 20 more here added, that minus 20, that we call a hyperpolarization. Okay, so that means when I touch, that area will become like this, minus 70 to the minus 55 to the plus 45 to the minus 70 to the minus 90, then it back to the normal position. This is a total story of this area, but we need to go for little additional. That here, simply if it is a Neet NCRT textbook, when you follow, this is enough for us. This thing is happened. That means resting state to the depolarization state is because of influx of sodium ions. That's all. And repolarization to the hyperpolarization due to the efflux of potassium ions. This is enough for us. That means we already said that influx of sodium ion, charge increases, efflux of potassium ion, charge decreases. This is enough for us actually, but we need to continue with the state textbook here. It was given with the gates. Now let me introduce the gates to you. This is over actually. If it all stop here, this is over, but we have some extension in the state textbook. That about the activation and inactivation gates, we said till the time sodium will come inside, potassium will go outside, isn't it? But to come inside, to go outside, there is a membrane we have in between. What is that membrane? That membrane we say axolemma. The membrane of axon we say axolemma. So the going and coming is not so easy. That will happen through the gates. We have some separate gates here. So through that gates only the thing is going and coming. So that particular gates are having some specific names that I have to introduce that specific names to you. That the sodium inactivation gates, sodium activation gates, sodium inactivation gate and sodium activation gates and potassium voltage gated channels. Now I am introducing the potassium voltage gated channels and sodium inactivation gates and sodium activation gates to you. Okay, so like this. Sodium and sodium inactivation gate, sodium activation gate, potassium voltage gated channels. Okay, so I'll show you that particular channels to you. I'll show you. Let me show. Just give me some 30 seconds time. I'll share the diagram which we have in our textbook. Yeah, here it is. This is the diagram. Okay, so now learning the topic through this diagram. That same topic we are learning through this particular diagram. So now let me show you first of all where does the inactivation gates and activation gates are present. You see this is the resting state. Okay, let me use another color. This is the resting state. We are showing gates, only gates. Okay, so in this area, if that I'll draw here that you may understand this properly. Like this it was given and like this it was given. Means you need to understand if it is open like this, like this. You need to understand this is open. Here, this area I'm showing. That sodium inactivation gates they are. Okay, we need to label them, otherwise you can't understand the diagram. Sodium inactivation gates they are. This is sodium activation gate. Okay. Sodium inactivation gates are open. Sodium activation gates are closed. So I'll show you each and every diagram to you. Then we'll write some information above there. That let me zoom that area. Only resting state. Just focus only that area. Okay, so resting state, let me write the information about the resting state. Okay, let me write the information about the resting state. It's better we use red color. So we are talking about resting state. Sodium inactivation gates are open. I hope you can see. Sodium inactivation gates are open. I'll take little bit bigger. Yeah. Sodium inactivation gates are open. So I do label also here. Sodium inactivation gates are open. Next, number 2. Sodium activation gates are closed. Sodium activation gates are closed. Sodium activation gates are closed. That means this one. Sodium activation gates are closed. Okay. So beside, you see one more, isn't it? There is one more. Who is that? Potassium gates. This one, number 3, this one. Potassium gates are closed. Potassium gates are closed. Okay, so that sodium inactivation gates are open, sodium activation gates are closed, and potassium gates are closed. That is the condition in resting state. So let's come back and let's write that information on the whiteboard where we learned this particular concept, that voltage gates. Okay, so we learned just in the form of influx of sodium ion, influx of potassium ions, isn't it? So now I am making this information more productive here, that with the sodium gates. Okay, so let me write in resting state, in resting state. So the total, the complete notes you will get here now in resting state. So the conditions. Conditions. What we said about the condition, that charge outside, charge inside, that everything will write here. Everything will write in resting state. The charge outside is, if you are able, you can say outside, nothing but ECF. If you are able to say, you can say charge outside ECF. Positive or negative, you have to say. Positive. Charge inside. Charge inside. That means in axoplasm. In axoplasm. What is it? Negative. In axoplasm, that is negative. Okay. Next, what are the other things we learn here? Voltage in axolemma. Voltage in axolemma. That means resting membrane potential. We'll write like that. It will be better. Resting membrane potential. What is the resting membrane potential? Minus 70 millivolts. Okay, minus 70 millivolts. Next, the additional. This is up to Neet. That means that the issues we learned here up to Neet. And now you people need to learn the new things here, which is given in the state textbook. That is about the sodium inactivation gate, sodium activation gates, and potassium voltage gated channels. So sodium inactivated gated channel, sodium inactivated gated channels are open. Then next, sodium activated gated channels are closed. Sodium activated gated channels are closed. Okay. Next, what next? Potassium voltage gated channels are. Potassium voltage gated channels are. The potassium voltage gated channels are closed. This is the condition in resting state. Resting state position is like this. Okay. Next, when the stimulus comes, when the stimulus comes, when this act that threshold stimulus, when threshold energy is making some disturbance there. So we have to see at the time what happens when threshold stimulus makes some disturbance there. That means the stimulus energy will bring the minus 70 to minus 55, will bring the minus 70 to minus 55, and then after that there is an influx of sodium ions, we said, isn't it? We said this as there is an influx of sodium ions. Maximum possible is this one, okay. There is an influx of sodium ions. Okay, for that what is required? There you can see in the depolarization that is shown over. Sodium inactivation gates are already open. Earlier even we are seeing. Sodium inactivation gates are open. Okay. Next, number 2. Sodium activation gates. Sodium activation gates also open. That we need to remember. Sodium activation gates are also open. There you can see there is an influx of sodium ions, isn't it? There is an influx of sodium ion. We say that charge increases. Okay. Next, the third one about potassium gates. About the potassium gates. So we are talking about potassium gates. They are still closed, isn't it? Potassium gates are closed. This is the condition during depolarization. This is the condition during depolarization. Okay, so let us write. Let us write, and also we need to see here there is a charge difference. That means when depolarization occurs, what is the normal condition? Actually, I'll write the normal condition here. That outside positive, inside negative, isn't it? Normal condition is outside positive, inside negative. But during depolarization, because of the influx of sodium, that what happened here, outside negative and inside positive. That is the reverse condition. We say how much positive, that we have answer for that, plus 45. Okay, that we need to write in the form of notes. So let me write. I'll go for the whiteboard. I'm going. Yeah. Okay. Next. Then what is our next in during the second heading? What is that? Depolarization. Resting state is called polarization. Now the depolarization. During depolarization, all the events which are related during depolarization, that we have to see. First of all, charge outside. If you are able to say, you can say charge outside. Charge outside. I said it will become reverse. That means charge outside negative. These are very important for Neet. Charge inside positive. How much positive? We have answer plus 45, isn't it? Then depolarization. This is all possible because of what? Because of influx of sodium ions. That it is enough for Neet to remember influx of, because in based on NCRT there is no gates information in NCRT. So how it is possible? We say because of influx of sodium ions. Okay. Then if we want to write about the information of the gates based on the state textbook, we need to write like this. That sodium inactivation gates are open. Sodium inactivation gates are open. Okay. Next, the sodium activation gates are also open. Sodium activation gates are also open. Are open. Then that's why influx of sodium ion is happening and charge increase. Next, potassium gates are still closed. Potassium gates are still closed. Okay. So this is the gate information. Okay. So that's it. This is during depolarization. Voltage during this particular time is said to be plus 45 millivolts. Voltage during this time is plus 45 millivolts. Okay, so that's it. This is all happened because of influx of sodium ions. Simply we say influx of sodium ion, charge increase. Okay, but how it is happened? It was given here because of the opening of activation gates of sodium along with the inactivation gate. So voltage condition during this particular period of time, even I'll show that inside positive outside negative because of sodium influx, inside positive, outside negative. Okay, that means that is reverse, that you need to understand. For that we need to draw a bigger one. Let me draw the bigger one to understand much better. So normal condition is outside positive and inside negative. So when we want to show the depolarization area, we'll show like this, that negative outside and positive inside. Then remaining same, remaining, that means at to go forward. So positive inside. So what do you say? This area is called depolarization. We call that area as depolarization. Okay. Next, let us go for the repolarization. Let's go for the repolarization. I am going. Okay, so now this is the area. Okay, yes. Then let me fix over. This is the area. Repolarization. Now just focus on repolarization. Here it is. Okay, so what you can see here, number that the gates. Okay, red better, I think. Red is visible. Red is blue is visible. No, red. Red is the best visible with little ink size. Okay. So what about sodium inactivation gates? Sodium inactivation gates are closed. So just observe them. Sodium inactivation gates are closed. This one. Okay, so then sodium activation gates are, they are open, but there is no use actually, because with both open only, that there may be a possible of influx. But what is this? This is repolarization, isn't it? What do you say this as? This is repolarization diagram. So what can be expected in the repolarization? Repolarization, there must be an efflux of potassium ion. So what we have to expect here, what we can expect here, that is very important for us, that what we can expect here, this one, that potassium gates are open. Potassium voltage gated channels are open. That is very important for us. Okay. Shall we change color for this? Is it clear? Okay, potassium voltage gated channels are open. So that is during repolarization. Repolarization means reaching back to the normal position again. Reaching back to the normal position again. What do you say? Repolarization. Okay, let me write the notes here. We'll go to the whiteboard and let us write that learned information. Let us write the learned information here. Number 3, repolarization. Okay, so that repolarization. So what we are writing will follow the same pattern. Charge outside, charge inside. So when we are going to say like this, the repolarization means normal condition, isn't it? Normal condition means again we have to say charge outside. Charge outside is positive. Okay, the charge inside, that is negative. Charge inside is going to be negative. Number 3, then voltage. So what we are writing in the number 3, that influx of sodium ions. We wrote in depolarization. So what we can write here, there is an efflux of potassium ion because we are getting back. So that's why efflux of potassium ions. Okay. So that will happen, a flux of potassium ion. So gates I am writing separately. That gates I am writing separately. That because that is not given in state NCRT textbook. So, but learning them will be much helpful for us actually. So gates, sodium inactivation gates are. Sodium inactivation gates are. Sodium inactivation gates are closed. So let me elaborate. Give me permission. Sodium inactivation gates are closed. Next, sodium activation gates are open. Sodium activation gates are open. Then the very important here, that is potassium voltage gated channels are open. That facilitate, you can understand, potassium voltage gated channels are open. Okay, so that is very important for us to remember. Potassium voltage gated channels are open. They only decrease the charge. So what is the charge at this time? That minus 70. We reached back. So where we are? That is also important, isn't it? Where we are? We are exactly in this location. I'll show you. Minus 70 we started, and minus 55 is the threshold. Then from minus 55 we reach to the plus 45. We call the total as depolarization. This is depolarization. Next, reaching plus 45 to minus 70 is called repolarization. Okay, so there is another step is to go, that is the minus 90, isn't it? That another step to go, that is minus 90. So we'll go there. That is hyperpolarization. So I'll show you the diagram back to you. That now this time we focus on hyperpolarization. Here it is. So hyperpolarization. So I think at least finally when we came here, that you can understand that hyperpolarization condition clearly. Let me show you. This is enough for us. Okay. Hyperpolarization. Sodium inactivation and activated gated channels are closed, isn't it? Sodium inactivated and activated gated channels. Activated gated channels are closed. Shall I show you? This is the area. Both are closed. Sodium inactivated and activated gated channels are closed. Then that observe this area. Potassium voltage gated channels are open. Because that's what we are saying. Potassium voltage gated channels are open. Okay, so potassium is, this is enough actually. We can write potassium. Potassium voltage gated channels are open. So that is very important. Yes. Potassium gated, voltage gated channels are open. Okay, this color is better. I'm writing bigger. So that's it. Hyperpolarization. So what is the voltage here? Minus 90. Hyperpolarization. We can say that as minus 90. Okay, now let's go back. So final notes, that is the fourth one, that is hyperpolarization. Reach to the normal position. Hyperpolarization means reach to the normal position. So how we define hyperpolarization? Reaching that still, and that means more efflux of potassium ions. That more efflux of potassium ions result that the condition reaches here, that particular status. What do you call this status? More than the normal state, more than the rest, we can say. More than the resting status. More than resting state. What do you say? Hyperpolarization. Polarization is the normal state. Okay, so that means I'll show you what is more than the resting state. Resting state means minus 70, but more than the resting state we are talking about. That means reach to minus 90. So what will be the voltage of this particular hyperpolarization? Minus 90. What is the advantage? Advantage, I said to you in the form of assertion reason, like that if minus 90 plus 45 and minus 70, if it is there, that always the point of depolarization, behind the point of depolarization, the hyperpolarized status is present. For what? For what? To facilitate that impulse need to move, to make them to move only forward condition. That means to make the impulse always unidirectional, that before the depolarization, the status will be hyperpolarization. Okay, so gates wise, what we have to remember, the both sodium inactivation and activation gates are sodium inactivation and activated gate. Sodium inactivated gate and activated gate, both are closed. Okay, so who is open? Potassium voltage gated channels are still open. Potassium voltage gated channels are still open. Okay, so this is the condition. Okay, so that is about hyperpolarized status. Hyperpolarized status, then depolarization, repolarization, hyperpolarization. Here, the very important thing you people need to remember that we just the gates, the state examination point of view, it is very important for us to remember the gates is very important for us, very important for us, that to remember the gates. So, okay, I'll show the animation of this particular nerve impulse. Just wait for me till the time I am going to say the gates once again, that during, what's that, animation, nerve impulse, okay. So, okay, during, so the resting status, sodium inactivation gates are open. Sodium activation gates are closed. Sodium activation gates are closed. And potassium voltage gated channels are closed. That is the during resting state. And during action membrane potential, what happens? Sodium inactivation and activation gates are open, and the potassium voltage gated channels are closed. Okay, next, repolarization. Repolarization, sodium inactivation gates are open, sodium inactivation gates are open, the inactivated gates are closed.
A nerve
And
impulse is an electrical current that travels along dendrites or axons due to ions moving through voltage gates.
So what we said, repolarization, sodium inactivation gates are closed, sodium activation gates are open, and potassium voltage gated channels are closed. Then in case of hyperpolarization, both sodium inactivation and activated gated channels are sodium inactivated and activated gated channels are closed, and potassium voltage gated channels are open. Okay, so that's it. Okay, that animation is ready for you. That once you check this, then after we'll discuss.
The cell. This charged
Let's start from the beginning.
Is an electrical current that travels along dendrites or axons due to ions moving through voltage-gated channels in the neuron's plasma membrane. Voltage-gated channels open and close in response to an electrical voltage, so they are affected by changes in electrical charge around them. When a neuron is at rest, a charge difference is maintained between the inside and outside of the cell. This charge difference is produced and maintained largely by active transport using sodium-potassium pumps. The pumps send sodium ions out of the cell and bring potassium ions in. While other channels allow some flow of potassium ions back out of the cell, the sodium ions cannot easily get back in to replace the lost positive charges. The overall result is that the exterior of the cell has a net positive charge and the interior has a net negative charge. The difference in charge between the interior and exterior of the cell is called the resting membrane potential. A nerve impulse begins when a stimulus disturbs the plasma membrane on a dendrite, causing sodium channels to open. Sodium ions flow into the cell, lessening the charge difference at that location. If the change is enough, it will cause nearby voltage-gated sodium channels to open. This allows so many sodium ions to flood into the cell at that location that the membrane there is depolarized, with the local region inside the cell having a net positive charge and the outside of the cell having a net negative charge. This affects neighboring voltage-gated sodium channels, which then open, moving the depolarization along the membrane. This moving depolarization is called an action potential. Changes occur behind the action potential to restore the resting membrane potential. The voltage-gated sodium channels close and voltage-gated potassium channels open. This allows a rapid flow of potassium ions out of the cell, repolarizing the membrane so that the inside is again negative and the outside positive. This is followed by use of sodium-potassium pumps to fully restore the resting membrane potential and to reestablish proper concentrations of sodium and potassium ions inside and outside the cell.
Yes, that's about the conduction and propagation. We'll have some small
is at its resting membrane potential. The activation gates of the voltage-gated sodium ion channels are closed and the inactivation gates are open. Voltage-gated potassium ion channels are closed. Depolarization is initiated by a stimulus which makes the membrane potential more positive, causing the voltage-gated sodium ion channels to start to open. As threshold is reached, many sodium channels open. Sodium ions diffuse across the membrane, causing depolarization. Voltage-gated potassium ion channels also begin to open, but more slowly. Therefore, depolarization occurs because more sodium ions diffuse into the cell than potassium ions diffuse out of it. As the membrane potential approaches maximum depolarization, the inactivation gates of the voltage-gated sodium ion channels begin to close, and the diffusion of sodium ions decreases. The potassium ion channels remain open, and potassium ions continue to diffuse out of the cell. The increased potassium ion permeability lasts slightly longer than the time required to bring the membrane potential back to its resting level. The extra efflux of potassium ions causes the membrane potential to become slightly more negative than the resting value. After the voltage-gated potassium ion channels close, the active transport of sodium and potassium ions reestablishes the resting membrane potential.
So that's it.
When the cell membrane
That's it. Allow me to talk. You just talk till the time. Now this is my time. You see that some variation is there in different books, in different variations are there. But this is this particular is suitable for us, isn't it? This is suitable for us. So here, resting membrane potential. When we talk about the resting membrane potential, that what I said about the resting membrane potential, the resting membrane potential include, should take green, I think. So this is the area. And the sodium inactivation and activation gates. In the earlier animation, we have seen there seems to be separate. That is in different animation, different textbooks, different versions are there, but no matter for us. This will be better suitable for us. Let us talk about this. Is the point number one we are taken. Sodium inactivation gates are open. This is the point number two. Sodium activation gates are closed, and potassium voltage gated channels are closed. Is the condition we are taken or not? Resting membrane potential. Voltage at this time is minus 70. Have you seen behind on the screen? You can see this particular lipoprotein model, fluid mosaic model of the Singer and Nicholson, because it's just a cell membrane. So this is a cell membrane, a special kind of cell membrane which having special gates which allow only sodium ions, which allow only potassium ions. That's why on their name, they just named like that, sodium, the potassium voltage gated channel and sodium voltage gated channel. In that way, we just named them as. Okay. So that is the first issue that we need to understand. So what I said, let me show you once again. Let me erase this. So I'm labeling this. You just watch this. So this is, what is this? Sodium activated gated channel. Sodium activated gated channel. So what happened to the sodium activated gated channel is closed. Sodium activated gated channel is closed. Okay. Next, this one. Sodium inactivated gated channel. So during resting membrane condition, sodium inactivated gated channel is open, isn't it? It is open. Sodium inactivated gated channel is open. So what left over? The potassium gated channel, this one. So potassium gated channel. So this potassium gated channel is closed. So what do you say this as? Potassium gated channel is closed. This is potassium gated channel. Okay, so that is voltage gated channel. No matter that at least you need to understand that was flow. So this is the condition during resting membrane potential. Sodium inactivation gates are closed. Sodium uh, inactivation gates are open. Sodium inactivation gates are open. Sodium activated gated channels are closed, and potassium voltage gated channels are closed. So this is the condition that you need to remember. Okay. So let's move on. When we move on, there you can see the resting membrane when threshold stimulus. So shall we talk about that particular ionic distribution outside and inside? What we said, who is more outside? You see more sodium ions are present outside and some potassium are there, but more sodium. Sodium is 10 times greater in resting status. Outside means that is in ECF. Okay. So inside, this is axoplasm. Inside, who is more potassium ion? See that violet balls, all they are potassium ion. Okay, some sodium ions are there, isn't it? Some sodium. That means for every 10 sodium ions, one sodium ion inside. For every 30 potassium ions inside means axoplasm, one potassium ion outside. So that is the condition. Okay. Okay, let's continue. What happens after this? Let us see. So what is happening when the stimulus energy, we just talked about the threshold, amount of stimulus energy which required to conduct an impulse. We just touched that brings the sodium activation gates are open. So that sodium activation gates are open, there is an influx of sodium ion. We should say this as influx of sodium ions. There is an influx of sodium ions, which what we said the charge will be increased. Initially minus 55 due to threshold. So finally the charge inside will increase up to plus 45. So we said about depolarization, we reach from minus 70 to plus 45 due to the influx of sodium ions. Okay, now moving on. There you can see the influx of sodium ion. Okay, that's over. Depolarization is over. So what can be expected after moving the potential energy forward? What can be expected in that area? Repolarization. That means charge need to decrease. For that, what is required? Charge need to decrease. That means For that, potassium ions need to move far outward. A flux of potassium ions slowly started. So what do you call the flux of potassium ion? Repolarization. That's why that plus 45 again slowly it reaches towards the minus 70, a flux of potassium ion. But after reaching minus 70 even, after reaching minus 70 even, what is happening? Still the potassium ions are going. That's why voltage will go for little more decrease, that we say hyperpolarization. Then still potassium ions are going, that we say still hyperpolarization. Okay. So that you can see in the end hyperpolarization. So the finally, this is all about that particular issue, that depolarization, repolarization, the depolarization, repolarization, and hyperpolarization. Let us give some conclusion today by the voltage differences, whatever we are seeing at present. Now let's go for some conclusion here, and then we'll discuss about the conduction and propagation of nerve impulse tomorrow in the classroom. Okay, let me close this. Only the graph we'll discuss about this today. About the graph. Okay. So now let's talk about the graph. So the graph is visible to you here. That first of all, let us try to recognize. Let us try to recognize in the graph. So what color will take? Okay, red color. So this is the first one. So just observe where I am showing. Okay. So minus 70. That is it correct or not? Well, see the graph. Minus 50, minus 100. So these points, it will be minus 70. Okay. So this minus 70 will go by the stimulus. The second one is threshold stimulus. That because of the threshold stimulus, what happened? Influx of sodium ion that reached, the charge increases. That is the depolarization. Okay. Next, after that, due to the efflux of potassium ions, the charge is decreased. We say it as repolarization. More decrease, we call hyperpolarization. We came up to here minus 90. Then after reaching to the normal position. So I'll show you once again here also. So this is depolarization. We are at minus 70. Threshold, a little increase. Then after influx of sodium ions is given here. Then because of that influx of sodium ion, charge increased up to minus 70. That was shown here in the diagram. Sorry, plus 45. That was shown in the diagram. Okay, plus 45. Then after getting down, getting up to here, we say repolarization, reaching up to minus 70. But we didn't stop. Little more down, that is minus 90. Then after reaching to the normal position. So that's it. This is the very, very frequent area for questions in examination. This is a very frequent area for questions in examination. That means they'll ask like this. Number 4, what is happening at number 4? Efflux of potassium ion, charge decreases. What is happening at number 3? That in Neet we get these kind of questions. They don't ask about the gates, but learning about the gates will help us to understand this much better. Okay, so here in the given diagram, let me close this. In the given diagram, number 1 is resting state. Number 1 is resting state or resting membrane potential. Number 2 is threshold. Number 3 is depolarization. That means number 3, depolarization. Should understand that, should remember that events, what is happening during that particular phase. Number 4, repolarization. That is repolarization. Number 5, hyperpolarization. Number 5 is hyperpolarization. Okay, so that's it. That is the total story of this conduction and propagation of nerve impulse. We have to discuss this. We'll go with more information on this area and we'll revise and we'll repeat. We'll go with some more issues which are related to this conduction and propagation of nerve impulse, like refractory period, like synaptic potentials, that all we'll discuss in the next class. Okay, so